Hi, everybody. We are starting series parallel circuits now. So we did series circuits, we did parallel circuits, we've done fairly well. So now we're going to mesh all of that learning together to get into series parallel circuits. Okay, so we're going to start off by following the current in this circuit. So what we have here is R1, R2, and R3 and E. Okay, so as always, IT leaves our power supply and comes back. Okay, so that's IT. That is always IT in any circuit. Okay, the current leaving the power supply and the current coming back to the power supply is IT. So what happens here now is R1, since this current is the same as that current, okay, since it's the same, we know that R1 is in series with the power supply. All right, now what we have here is our current gets to this junction and R2 and R3 are in parallel. So now we have current coming this way and rejoining over here. So now this current here is IR2 and this current here is IR3. All right, so let's analyze this circuit, or as I like to do, let's overanalyze it. So let's talk about relationships here. Let's talk about relationships. We know, all right, we know that R2 is in parallel with R3. Okay, we know that R1 is in series with E. Okay, so we know that. So this is the most basic series parallel circuit. Now, since R2 is in parallel with R3, and we know that parallel voltages are the same, then we know that, therefore, VR2 is equal to VR3. All right, we know that. Now, we see IT coming into this parallel branch, and it's splitting up into IR2, IR3, and it's coming back. So using Kirchhoff's current law in a parallel circuit, we know that IT is equal to IR2 plus IR3. All right, so these are things that we know about this circuit. Okay, we know that. So we have, we also have here a loop over here. So we have this loop, and we'll call this loop A. Okay, so for loop A, so this here is Kirchhoff's current law. Okay, we know that. So for loop A, if we were to take, we'll mark our polarities down. Okay, if we were to take this loop, we know that E minus VR1 minus VR2 is equal to 0. Okay, and that is Kirchhoff's voltage law, if you remember. The algebraic sum of voltages in a loop equals 0. So E minus VR1 minus VR2 is equal to 0. We also have another loop here. It's this loop. It's the loop that involves R1, R3, and E. Okay, and we'll call that loop B. So loop B is E minus, so loop B involves R1, R3, and E equals minus VR1 minus VR3 equals 0. And that is also Kirchhoff's voltage law. All right. Now, there's a third loop here, And it may seem obvious, but we're going to say it anyways. But there's a third loop, and it's here. Okay, and this is loop C. That is loop C. So not every loop needs to have a power supply connected to it. Not every loop needs to have a power supply connected to it. So loop C tells us that VR2 minus VR3 is equal to 0. And that is also Kirchhoff's voltage law. Okay, this is going to come into play when we do more complicated circuits. Now this equation here lends itself to that. Okay, so if we were to move VR3 to the other side of the equal sign, we would get VR2 equals VR3. All right, so in this circuit, we know that R2 is in parallel with R3. And we know that this together is in series with R1. Okay, we know that that is true, that R2 in parallel with R3 together are in series with R1. So RT in this circuit is R1 plus R2 in parallel with R3. Okay, so that is something very important to know. All right, now that we have RT, we can figure out IT, because we know that IT is equal to E over RT. Okay, and that is Ohm's law. So when we're going through these series parallel circuits, we're going to keep referring back to the different rules that we learned about different functions, okay, about different circuits. So we know that IT is that. Now, because R1 is in series with E, we can use the voltage divider rule to figure out VR1, okay? So VR1 is equal to IT times R1, okay? And that is Ohm's law. But it's also equal to, R1 over RT times E. And that is the voltage divider rule. Okay, that is the voltage divider rule. So far we've brought forward 1, 2, 3 of the rules that we learned in the series and parallel circuits. So we know VR1, okay? How can we figure out VR2? Well, we know E, and we know VR1, and we know this makes a loop, okay? So we can say that VR2 is equal to, if we go back to loop A says that E minus VR1 minus VR2 is equal to 0. Well, if we move VR2 to the other side of the equal sign, we would get VR2 is equal to E minus VR1. Okay, and again, that is Kirchhoff's voltage law. And we know that VR2 is equal to VR3, okay, because they're in parallel. But what else do we know here? What else do we know? Well, we can say that, here, we can also figure out, if we want to do IR2 is equal to VR2 over R2, okay? And that is Ohm's law. All right, but we could also say we know the current We know the current coming into this parallel branch. We know we have two resistors in parallel. So how is this current distributed among these two resistors? And if you recall, we had the current divider rule. So what we're going to say here is that IR2 is equal to R2 in parallel with R3 over R2 times, in this case, it's IT going in there. Okay, so if you recall, when we're doing parallel circuits, just straight up, we were saying that the current divider rule is RT over that resistor times IT. But in this case, because this is our only parallel part of the circuit, we don't say RT because RT is all this, but we do say the total resistance of this network, of this parallel network, divided by the resistor we're looking for times the current coming in. Okay, so it's something important to remember. It's something very important to remember, and we're going to keep beating on that over the next three examples. So we have IR2. So IR3, we have three ways to figure out IR3. IR3 is equal to VR3 over R3. That's Ohm's law. Sorry, this is the current divider rule. It's also equal to R2 over, or R2 in parallel with R3 over R3 times IT. Okay, and this is the current divider rule. And this is Ohm's law, as I said before. And then the last way, or we could say that IR3 is equal to IT minus IR2. And that is Kirchhoff's current law. Okay, so we have implemented here Kirchhoff's voltage law, Kirchhoff's current law, and voltage divider rule and the current divider rule. All right. So how does this work? So let's do a working example here. Let's do a working example. Now, what you have to remember is that this circuit needs to tell a story that makes sense. Okay. So let's get to work here. We're going to say, let's find RT first. Okay. RT is equal to R1 plus R2 in parallel with R3. So that is equal to 1K plus 2K in parallel with 3K, which is 1K plus, and if we do that quickly in our calculator, it would be 2K 1 over plus 3K 1 over equals, and 1 over the answer, and I get 1.2K. So RT is 2.2K. All right. So now IT is equal to E over RT equal to 10 volts over 2.2K. All right. And what do we get there? 10 divided by 2200, 2.2K. So I get 4.545 milliamps. 4.545 milliamps. So let's start drawing our story in. IT is 4.545 milliamps. Okay, nice. Now, VR1. What is VR1? Let's just do it quickly. IT times R1, which is 4.545 volts. Okay, this current going through that resistor is 4.545 volts. So let's draw that value in here. 4.545 volts. All right, that's what we have there. Now, VR2, if we use, so here I'm going to say Ohm's law. All right, that's what I use there. Here too, Ohm's law. Now, VR2, let's use Kirchhoff's voltage law. We have a loop here. We have a loop. So we could say that VR2 is equal to E minus VR1. So VR2 is equal to E minus VR1 equal to 10 minus 4.545 volts. Okay? Which gives us we get that, and we have 5.455 volts. Okay, so I'm going to write in here 5.455 volts. Okay, now we also know that VR3 is equal to VR2 because they're in parallel, equals 5.455 volts. All right, so that's what we have there. Now, let's figure out IR2. IR2, if we just use Ohm's law quickly, IR2 is equal to VR2 over R2, so it's 5.455 divided by 2K. And what do we get there? Divided by 2K, 2.728 milliamps. 2.728 milliamps. Okay? IR3, let's use Ohm's law there as well. VR3 over R3 equals 5.455 over 3K, all right? And that gives us 5.455 divided by 3K, 1.818 milliamps. All right, so what we've done there is we have figured out the current for each of these branches. Okay, so what we have here is 1.818 milliamps and 2.728 milliamps. All right, so the story makes sense here. These two voltages are the same. These two currents, if we were to do Kirchhoff's current law, IR2 plus IR3 is equal to 2.728 milliamps plus 1.818 milliamps, and that would equal 4.546 milliamps, okay? Which is approximately equal to IT, which it should be, okay? In this case, it's IT. We're gonna see later that's not always IT that we're using there. So that's what we get there, okay? So this story makes sense. This loop, these two add up to 10. These two add up to 10. These two currents add up to IT. So our story makes sense here. This follows the rules of parallel circuits, where parallel voltages are the same and parallel currents will add up to the current going into that network. So like I said, when the current comes out here, when the current comes out over there, it is 4.545 milliamps. Okay, so that all works out. All right, so if you need to go over that again, stop the video and rewind it. Stop the video and rewind it. and just to review it one more time, okay? So now we're going to get into this configuration. Here, okay? So let's write down what we know about what we see here. This is a different configuration. Now, one thing I'm going to tell you, now that I brought up the second one, is you need to understand how this works. You don't need to memorize it. When we're doing series circuits, R1 plus R2 plus R3 equals RT, current is constant, VR1 plus VR2, blah, 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 equals E. And then for parallel circuits, you know, IR1 plus IR2 plus IR3 is equal to IT, and VR1, VR2, VR3 are all equal, and RT equals 1 over R1 plus 1 over. So those were things you kind of memorized, but now we need to take those fundamentals and bring it into this. Bring it into this here, where you need to know what's going on. Okay, you need to understand how Kirchhoff's voltage law works. You need to understand how Kirchhoff's current law works. You need to understand the voltage divider rule and the current divider rule. You need to understand the properties of series circuits and the properties of parallel circuits. And having said all that, you also need to take a deep breath and give yourself enough time to practice and learn this. So don't just give up the first time you see one of these circuits, okay? It takes practice, trust me. So what do we know about this circuit? What do we know about this circuit? Well, we know that R1 is in parallel with E. R1 is in parallel with E, which tells us, therefore, if R1 is in parallel with E, we know parallel voltages are the same. So that tells us that VR1 is equal to E. Okay, that is very important to know that. All right, so what else do we know? We know that R2 is in series with R3, because if we follow our current, this is IT, all right? As I stated in previous lectures, the multicolor presentations are no extra charge. So we know that we have a current here, which is IR1, and we have this current, okay? So this is IR1. This current here, we're going to call IR2, R3. These are in series, all right? Here's something you need to understand. These are in series, which means R2 series with R3, okay? And what do we know about series circuits and current? Therefore, IR2 is equal to IR3. Okay, you need to know that those two currents are equal. All right. Now, these two together are in parallel with R1. All right, these two together are in parallel with R1, which tells us that, so if R2 plus R3 are in parallel with R1, that tells us, therefore, that these two voltages add up to equal VR1. So we know that VR1 is equal to VR2 plus VR3, okay? Now, if you started to smell something and what you're smelling is a possible application of the voltage divider rule, you're right. So what we have here is, we have all these principles, okay? We have all these principles here. So what do we know about this circuit now? To take these and go further. So we know that RT is equal to R1 in parallel with these two together, R2 plus R3. All right, we know that. So we know that IT is equal to E over RT. Okay, we know that. That's Ohm's law. Now, we know that VR1 is equal to E. We know VR1 is equal to E because they're in parallel. We also know, because these two are in series in parallel with R1, that VR2 plus VR3 is equal to VR1, also equal to E. Okay? So let's take Kirchhoff's voltage law in here. So let's call this loop A. Okay? So just as we did in the first example, loop A is, I didn't mark the polarities before, plus, positive, negative, positive, negative, positive, negative. Okay? So loop A is that E minus VR1 is equal to 0. And that is Kirchhoff's voltage law. We also have a loop B. Let's call it this. Okay? And loop B tells us, loop B translates into this here. Loop B says that VR1 minus VR2 minus VR3 is equal to 0. And that is also Kirchhoff's voltage law. All right? Then we have loop C here. We have this big loop, C. And loop C says that E minus VR2 minus VR3 is equal to 0. Okay? So the reason why I said you need to understand these and not memorize them is we have R1, R2, R3 in two completely different combinations here. So over here, we said that VR1 was equal to R1 over RT times E. But that's not the case here. Here, R1 is just equal to E because they're in parallel. Here, R1 was in series with E, and here it's in parallel with E. All right? So IR1 is simply VR1 over R1. Okay? But we can also say we have IT in this network. We can also say that IR1 is this whole resistance here, this entire resistance. So in this case, we're going to say that it's R1 in parallel with R2 plus R3 over R1 times IT. Okay? And that is the current divider rule. And this here is Ohm's law. All right? So using Kirchhoff's current law, we could figure out the current here by saying I of R2, R3 is equal to, well, we know the current coming in here, and we know the current down this branch. So we could say that it's IT minus IR1. Okay? IT minus IR1. And that is Kirchhoff's current law. So if you can see what I'm talking about, you have to understand how it works. You just can't memorize what R1 equals, what R2 equals, what IR3 equals, because it always changes depending on the circuit. Okay, so what is VR2? We could say that VR2 is equal to I R2 R3 times R2. We could say that. Ohm's law. And there's nothing wrong with using Ohm's law. You just can't always use it. You don't always have it available to you like that. Okay? But what else do we have? We can also say that we know these two resistances are in series. Okay? We know the voltage across these two resistors because it's the same as R1. And we know because they're in series that the voltage across these resistors is going to be the same ratio as the ratio of these resistors. So we'll say that VR2 is equal to R2 over R1 plus R2 times the voltage across this network, which is VR1. Okay, which is VR1. And that is the voltage divider rule. Okay, so that's how we apply those. All right, if you need to review that, pause the video and go back and listen to it again. Okay, but now we're going to do an example. Now we're going to do an example. So we have these values here, 10 volts, 1K, 2K, 3K. All right, so RT is equal to R1 in parallel with R2 plus R3. Okay, which in this case is equal to 1K in parallel with 2K plus 3K, which is 1K in parallel with 5K. Please don't ask me how I got 5K. Please. I'm just kidding. So 1K in parallel with 5K. So what do we get? We get there, okay, 1K parallel with 5K. And we get 833.333 ohms. There. Now, we can say that IT is equal to E over RT, which in this case is 10 divided by the answer, and we get 12 milliamps. So if you want to see the first difference already in understanding instead of memorizing, all right, we have the same three resistors, but in the last example, these three resistors were organized in a different, R2 and R3 were in parallel in series with R1. Now R2 and R3 are in series in parallel with R1. So we get a totally different RT. We get 833 ohms, 2.2K. All right, so that's why you need to understand, not memorize. Okay, so we have IT. We can find IR1. We can find IR1 by saying E over R1, which is 10 milliamps. It's 10 milliamps, okay? And then we can say I of R2, R3 is equal to IT minus IR1, which would be 2 milliamps. Okay, or you could say that it's equal to E over these two combined, because these two together are in parallel with E. So E over R2 plus R3, which is 10 over 5K, which is 2 milliamps. All right. On your calculator, you cannot do E divided by R2 plus R3. You need to have brackets in there or you're going to get the wrong answer. Right? Also make sure when you're doing the subscript notation that you keep R2, R3 a little smaller and below the I, so we know that it's a subscript. Because if it gets too big, you might end up saying, okay, this is IR2 times R3. And that's not how it works. Now, so let's draw what we have here. We have current, which is 12 milliamps, 10 milliamps, and 2 milliamps. Now, according to the current divider rule, does this make sense? Well, 5K is 5 times greater than 1K, and IR1 is 5 times greater than IR2, R3. So the current divider rule does apply there. It does work. It always works. It's a rule. Now, VR2, VR3. Okay, we know that VR2 plus VR3 is equal to VR1, also equal to E. Okay, because of this loop and because of that loop. And because these two together are in parallel with R1. R2 plus R3 are in parallel with R1. Okay, so to find VR2, we could use the voltage divider rule and say that it is R2 divided by R2 plus R3 times VR1. Okay, so what do we get there? We get 2K divided by 5K times 10 volts, which works out to be 4 volts. Okay, it works out to be 4 volts. VR3, if we want to do the same thing, is R3 over R2 plus R3 times VR1 again, which is 3K over 5K times 10 volts, and that is equal to 6 volts. So let's put our story together. This is 10 volts. VR2 is 4 volts, and VR3 is 6 volts. Okay, so a few things need to recognize here. One is that 4 plus 6 equal to 10. So this works here, Kirchhoff's voltage law. And we also see these are in series. R3 is 1.5 times greater than R2. And VR3 is 1.5 times greater than VR2. Okay, so all of these rules that we've been doing, Kirchhoff's voltage law, Kirchhoff's current law, voltage divider, current divider, Ohm's law, everything is coming up in a big ball in this unit. Okay, so I remind you again to understand it and practice it. Do not memorize it. Okay, because the circuits you're going to get in the test will not resemble the circuits we did in class, because they are going to test your understanding, not your memorization. Okay? Let's do one more, and then we'll wrap this up. This here, we have this circuit, okay? We have IT, we have these two branch currents, and we know this is IR2 and IR3, R4. So we added a fourth resistor in here, okay? So once again, we know that R1 is in series with E. R1 is in series with E. Therefore, IR1 is equal to IT. Okay, we know that. IT is passing through IR1, it comes out. So we know that. We know, let's think about this circuit now. R3 is in series with R4. Okay? R3 series with R4. Therefore, they're in series. Therefore, the current going through both is the same. I of R3 is equal to I of R4. All right? Capiche? So, we know that. Because these are in series and they are in parallel with R2, these are in series and in parallel with R2. That tells us that VR3 plus VR4 is equal to VR2. But unlike the last circuit, here, these two were in series, in parallel with this, and equal to E. Okay, that's because this parallel network was parallel to E. This parallel network is not in parallel with E because R1 is in series with E. Okay, that is a very important distinction to make, and one that demonstrates that you're starting to understand what we're doing here. Okay, so R2 is not in parallel with E. Okay, that's very important. Now, if we do our loops again, you've got to do the loops. We have a loop here, loop A. We have a loop here, loop B, and we have this loop here. And we're going to call this loop C. Okay, so we always are going to understand Kirchhoff's voltage law and the loops in these circuits. And when we start doing mesh analysis at the beginning of next semester, this is going to come into play even more. Okay, so loop A. Loop A, we have R1, R2, and E. Okay, and before I retire, I hope to remember to put the polarities on the circuits. There. So loop A tells us that E minus VR1 minus VR2 is equal to 0. Okay. Loop B, which is this big one, loop B has R1, R3, and R4, and E. So E minus VR1 minus VR3 minus VR4 is equal to 0. And then loop C here, similar to what we did last time, is equal to, VR2 minus VR3 minus VR4 equal to 0. Okay? And we're also going to say that IT is equal to IR1, because they're in series, and is equal to I of R2 plus I R3 R4. Right? And that is Kirchhoff's current law. Okay? So if we just want to make those notes there, this is Kirchhoff's current law, Kirchhoff's voltage law, Kirchhoff's voltage law, and Kirchhoff's voltage law. Okay? So we put all those through there. So, what do we know here? We know that IT is equal to E over RT, because it always is. All right? We know that R1 is in series with E, which means we can apply the voltage divider rule to R1, to VR1. So we could say that VR1 is equal to R1 over RT times E. Okay? We have this loop here. We have this loop here, so we could say that VR2 is equal to E minus VR1. Okay? We know that. Now, we can apply the voltage divider rule here. we can apply the voltage divider rule by saying that VR3 is equal to, so we know the voltage across both of these resistors together is the same as VR2, because R2 is in parallel with both of these together. So we can say that VR3 is equal to R3 over R3 plus R4 times VR2. And we can say that VR4 is equal to R4 over R3 plus R4 times VR2 again, right? Or we could say that it's equal to VR2 minus VR3. Okay, we could say that this voltage here is equal to the total voltage across the string, which is our VR2, minus the voltage at R3. Okay, so that's where we get there. Now, there are different ways to find this. We could have found VR3 by finding IR3 by doing IT minus IR2, and we could have used Ohm's law. And the way you figure out which formula to use is to create the voltage, current, resistor, power chart. Okay? So let's go to our last example. Let's go to our last example and work this out. So we have these values, 10 volts, 1K, 2K, 3K, 4K. All right? So RT. RT is equal to, if you remember what we wrote, what we're getting here, RT is equal to, these two are in series in parallel with this. So R3 and R4 are in series in parallel with R2. Okay? And all of this together is in series with R1. All right? So actually, I didn't write it back on the other sheet, but RT is equal to here, R1 plus bracket R2 in parallel with bracket R3 plus R4. Okay, so these two are in series. All of that is in parallel with this. These two are in series in parallel with this, and all of this, which is these big brackets here, are in series with R1. So we get 1K plus 2K in parallel with 3K plus 4K. You need to do what's in the brackets first. If you don't put brackets, you might accidentally say R2 in parallel with R3, so 2K in parallel with 3K equals 1.6K or whatever it works out to. And those two are in series with R4, which is wrong. Okay, so the brackets are a big deal. So we have here 1K plus 2K in parallel with these two together, 7K equals 1K plus, so 2K in parallel with 7K is we have 2K plus 7K parallel, 1 over, so we get 1.556K. So we get 2.556K. Now, if there's a pitfall that people fall into, is they will do this and they'll stop there and say, okay, that's RT, but you forgot to add this last resistor. So we have RT, okay? Let's find IT. IT equals E over RT equals 10 volts over 2.556K equals 10 divided by 2.556K equals 3.912 milliamps. Okay, So let's start putting our story together. We have IT 3.912 milliamps. And we have IT coming back, 3.912 milliamps. And we also have IT coming in here, right? 3.912 milliamps. Great. Now, what can we do? Okay, let's take a different approach this time, just because we can. And let's find IR2 and IR3, IR4 without knowing the voltages first. So what can we use here? We don't know any voltages, so we can't use Ohm's law. But we can use, we know there's a parallel network and we know the current going in. So that is a perfect setup for the current divider rule. Okay? So what we can do is we can say IR2 is equal to this resistance of this whole network, which is R2 in parallel with R3 plus R4 over R2 times IT coming in. In this case, it's still IT, okay? So what we get here is this network here we figured out before is 1.556 over 2K. This should have been kilo ohms. I'll fix that when I post it. It should have been kilo ohms. And all of that times 3.912 milliamps. So we have 1.556K divided by 2K times 3.912 milli. Okay, so we get there is 3.044 milliamps. Does that make sense? Does it make sense that it's that high? We have 3.912 coming in to this network and 3.044 milliamps down R2. Does it make sense that a majority of the current is going through R2? And the answer is a big fat yes, because R2, this branch has a resistance of 2K. This branch has a resistance of 7K. So of course this one will have almost 3 times more current than this one. Okay, so I of R3, R4, we can use Kirchhoff's current law by saying that it's IT less. Okay, so this here is 3.044 milli. And now we'll figure out this current. So IR3, R4 is IT minus IR2, which is 3.912 milli minus 3.044 milli. Okay. That's what we get there. And we get 868 microamps. Eight hundred and 68 microamps, okay? Or 0.868 milliamps. So it does make sense that more current is coming down here than here, okay? So let's start figuring out our voltages now. Let's start figuring out our voltages. VR1 can be IT times R1, which is in this case 3.912 volts. Okay, VR2 would do Ohm's law through the whole ways because we know all the currents and the voltages is IR2 times R2, which is 3.044 milli times 2K is 6.088 volts. So 3.912 volts for VR1, 6.088 volts for VR2. So does this loop make sense? Is 10 minus 3.912 minus 6.088 0? Let's have a look. 10 minus 3.912 minus 6.088 0. Okay, so it works. Then VR3 is equal to IR3 times R3, which is 868 micro times 3K. Oh, made a mistake there. 868 micro times 3K is 2.604. Okay. 2.604 volts. And then VR4 is equal to IR4 times R4, which is, again, 868 micro times 4K, and we get 3.472. All right, does this story make sense? Do these two voltages add up? The VR3 and VR4, do they add up to VR2? Well, 2.604 plus 3.472, so 6.076. So it's off by a bit because of decimal places. Did I add the right numbers? So we have that. But what about Kirchhoff's voltage law? What about Kirchhoff's voltage law? Okay, did that work? What do we get for this big loop? E minus VR1 minus VR3 minus VR4. 10 minus 3.912 minus 2.604 minus 3.472. Okay, so we get 0.012 volts. So we're there. Okay, so the story that we came up with makes sense from an electrical point of view. And we implemented here, we implemented the current divider rule and Ohm's law and Kirchhoff's current law. Okay, that is a lot of what we did here. So these are 3 examples that I wanted to cover for series parallel circuits. So in our next lesson, we're going to have slightly more complicated circuits where you are really going to have to see where the current divider rule and the voltage divider rule and Kirchhoff's current law and Kirchhoff's voltage law come into play and help you solve a circuit. Okay, so I encourage you to go through this, pause it if you don't understand it, and just rewind a little bit. And we'll see you next time. Thanks.